Alright, trig class, we're going to look at our first conic section, which is the ellipse. So this is the standard equation for an ellipse. X squared over a squared plus y squared over b squared equals 1. Alright, if we multiplied, if we had cleared fractions here, and we multiplied both sides of this equation by the common denominator, a squared, b squared, we would get, you would see what happened if you envision I multiplied by a squared, b squared here. The a squares would cancel and I'd have b squared x squared plus, again the same thing would happen here, the b squares would cancel and I'd have a squared y squared equals, and then on this side I multiplied by the denominator's product, so I would get a squared b squared. So what we would have there is x squared plus y squared with different coefficients, assuming a and b are different, equals something squared. So we'd have x squared plus y squared equals something squared, like r squared. So it's almost like the equation of a circle. It's just a and b are different. Okay, if a and b happen to be the same thing, let's move this down to 4 and move the b up to 4. If I can get it to, there we go. Oops. So 4 for a, 4 for b. If I do that, you notice these guys just become, everything converges and we end up with a circle. And this point is just a point floating around on a circle. Okay. This third point C is defined mathematically to be the square root of a squared minus b squared. And so since a and b have converted, they're the same, a squared minus b squared would be 16 minus 16, which is 0. So those 2 points went away. Or they became the origin. So that's what we're seeing right here. But when they differ, when we have different values in the denominator, let me make this 3. I want you to see the this is called the minor axis because 3 is smaller than 4. The y-axis is the minor axis, and our intersections are -3 and +3. All right, the value of b, all right, which is under y, and the major axis, which is it's called that because it's longer. -4 to +4 is longer than -3 to +3, so this is the longer axis. That's called the major axis, and a, the number that's being squared underneath the x squared, is the bigger number. So these 2 points are the endpoints of what we call the major axis. The other two are the endpoints of what we call the minor axis. And then these values of c now, because C is always on the major axis. These are called the foci, and they'll always be on the same axis as what we call the vertices of the ellipse, and the vertices are the endpoints of the major axis. So the foci will always be on the major axis, and those are the plus and minus c. So c 1.33 and I'm sorry, C is just the coordinates of this black point. I have C1 and C2 are my foci. So a squared minus b squared, in this case, the square root, and then the negative square root. So that's the 2.64 we're seeing, the negative 2.64. Sorry, I had those hidden. And then C is just this point, this black point that's on the curve. So this is what I have as C. But notice what happens is, as I move that point, D1 grows, D2 shrinks, or D2 grows and D1 shrinks. One grows, the other shrinks. Alright? And it's not just that one grows, the other shrinks. They grow and shrink at a rate that makes their sum always the same thing. Notice D1 is 2.677. D2 is 5.322. As I rotate around here, D always stays. D is the sum of the two distances. It always stays the same. It never changes. Alright? The sum of those two is always a constant. And that's what we mean by an ellipse. So if you have 2 points called your foci, and you define a distance from those 2 foci, and you stay constant, always have that distance, the shape that you would carve out as an ellipse. The sum of those 2 distances between the 2 foci is always the same. The shape that we would create with that definition is the ellipse. Alright, now what is D? What is that sum of the 2 distances? Well, notice right now A is 4. I'm going to make A go up to 5. So now I've moved everything out. I didn't change B, so we're still hitting it 3 and -3 on the y-axis. But I changed A, and so we went out further, so our ellipse got wider. Well, let's look at what D is now. D is 10. Alright, what if I make A be 6? Alright, so I stretched it out even further. What do you think it is now? It is 12. So when it was 4, it was 8. When it's 5, it was 10. When it's 6, it's 12. Well, what if I change B? Let's change B up to 4. Exactly 4. Alright, I move that around. So again, the sum of the distances is always the same. What's the sum of the distances? Now that we've changed A and B, it's still 12. Let me move this up so we can see it in real time as I'm changing it. When I change A, it changes along with it. Let me change it all the way up to, let's just go all the way up to 8. Now it's 16. Now watch what happens when I change B. Nothing happens to that distance. The sum of the 2 distances is always the same. So what is the sum of the 2 distances? The sum of the 2 distances, as you probably have already kind of figured out, is double whatever A is. And why is that? Well, because A is the endpoints of these axes. And when I rotate from here down, notice if you see D1 is starting from this focus and going to the point. So when I go all the way down, D1 goes from that focus all the way to that point. And D2 goes from this other focus to that point. But because of the symmetry of these 2 points, this distance D2 when I'm all the way down is also this distance over here, which is the only part of the major axis that is not covered right now, by those black lines. So when I go down, if I just pick up D2, remember D1 does go all the way over here, right? D1 is extending all the way to the point, and now the point is on the negative x-axis. So D2 could be picked up and just fill in that distance right there, and that's A, right? That distance right there from 0 to 8, that's 8, which is A. And then this is also A. So the sum of the 2 distances is always 2A. And it's always twice whatever this is. And that's again, that's the big definition of the ellipse. It's the distance between these 2 points, and these 2 points are specifically located to where the distance between one focus and a point on the curve, the other focus on the point on the curve, the combined distance is always twice the value of A. Now, if B were to ever be bigger than A, notice what happens here is if I drop this down below 6, the foci just move on to the other axis. So whoever has the bigger denominator, so 6 is bigger than 4. So now our minor axis is on the x-axis because the foci are now on the major axis. Okay, But when, and our ellipse will now be tall and skinny rather than, short and wide. All right, I've only got it set up to make the lines and the distances when it's on when the major axis is the x-axis. But just know that's what happens is we get those. The same thing would happen. We'd have points here, and the lines would be connected from the focus. Each focus. It's just now the foci would be on the y-axis if the y denominator were bigger than the x squared denominator. Okay, so anyway, I just wanted you to see the first visual of this, and then just know that we are going to graph these. We're going to find the foci. We're going to find the endpoints of the major axis, the endpoints of the minor axis. And as you can imagine, it is just square roots. These denominators are going to be squares, and typically they're perfect squares. So you'll see numbers like 16 and 9 and 25 and 36 and 49 and 60. You'll see perfect square denominators. But you don't have to. I mean, it could be x squared over 5. And so the endpoints of the horizontal axis would be negative square root of 5, positive square root of 5. So we're just taking square roots to find these points. But just know we're not going to see denominators that look like, 4 squared. We're going to see x squared over 16. And we'll just have to know we need to take the square root to get these numbers. All right, let's look at a few examples in the next video.